Alright, okay. Assalamualaikum dan selamat petang. Good afternoon to all. Okay, this is differential equation modeling chapter. Alright, so this is the first example, radioactive decay. Okay, when we deal with differential equation, lots of the problem involve modeling. So you have to understand how to model from the given problems. Okay, we have several problems. So this is one of the example. So radioactive decay. So let's say an experiment showed that rate of decay the number if decreasing. Okay, so the rate of decay of radioactive substance is proportional to the mass. Okay, the rate of decay is proportional to the mass of the substance. So first you read the problem. What does it say? So in this case, it says that rate of decay of a substance is proportional to the mass. Okay, so we are talking about the mass. Okay, let's go read the whole paragraph. So starting from the amount of the substance of 2 gram at time t0 from the starting point, what can you say about the amount of the substance in the future? So now the problems talk about the substance, okay, the radioactive substance. So let's say we call the radioactive substance as, let's say as B, okay, and B depends on the substance of 2 gram at time t0. So B depends on T. So what is B? So this is defined as, not equals to, but B is defined as the amount of substance, the radioactive substance, at any time T. Okay, so and next, the first paragraph says that the rate of decay of the substance. So the rate of decay, the rate of change of B, the substance B, is proportional to the mass. Is proportional to the mass. What is the mass? The mass is, this is the amount. So the mass is the same as the amount of substance. Okay, so it's proportional to B of T. Okay, so that's what is given to us. Alright, so we can change from before that I'm going to define, I'm going to rewrite, okay, what is dBdt. dBdt is the rate of change of the substance. Okay. Right. Okay. And we were given just now the rate of change of the substance is proportional to B of T. So what can we say about this? How to make this from a sentence problem to an equation? So you just change this. You have learned this in school, right? In high school. So this is equals to KB, right? So when you change the proportionality symbol to an equation, we have equals to and multiply with the KB. So what is K? K is proportionality constants. Okay, but if you read again the sentence given, it says that the rate of decay. So decay, the amount is decreasing. Okay, so to show that this rate is increasing, when you use either you know that K is negative, or to make it more understandable, so we're gonna assume K is always positive, and we add K is always a positive number, then we make it as negative K. Okay, so in this case K is always positive. Okay, like 2 minus 2, so it becomes negative. So the rate of change of B is equals to minus KB. So this is what is given. Okay, and you can solve this, right? So change it into, hold on, I'm going to, okay, oops, here. Okay, so I'm going to write, we can solve this. We can change, this is first order differential equation. You can change it into the general form of first order differential equation. So we're going to have dB dt is minus kb put on the other side. So plus kb is equals to 0. So first order ordinary differential equation, which is linear, and you should be able to solve this. But from the paragraph, it says that the amount of substance of 2 gram at time t0. So we have an initial condition where t equals to 0 and b is equals to 2 gram. Okay, b of t is equal to 2 gram. So this is what is given. So I'm sure using the previous, what we have learned previously, you should be able to solve this. Okay. I'm going to add in a page. Right, so we have this. Okay, so if we're going to solve this, so I'm going to rewrite it again. dB dt plus kb is equals to 0. So b of t is equals to, when t, I'm going to rewrite again when t equals to 0. So b of t is equals to 2. Okay. So you can either, I'm going to show you few, what you have learned before. We can separate it because this is dB dt equals to minus kb. So if you separate it, so it is minus kt, that's integrate. So you have ln b is equals to minus kt plus c, exponent both sides. So we have b of t is equals to a e to the minus kt, right, as a general solution. Or you can use, okay, I'm going to make it here. You can use integrating factor method, where we have your p, remember your function is b, your variable is t. So your p of t is equals to, your p of t is equals to k, and your q of t is equals to 0, right? Okay. And take the exponential function, the integrating factor, e to the power of k dt. So we're going to have e to the kt. Shortcut, d dt of, what is your function? B multiply with your integrating factor, e to the kt, is equals to, the right hand side is 0, multiply with the integrating factor is 0. Now next step is integrate both sides. Okay, so we have b e to the kt is equals to c, okay, and b is equals to c e to the minus kt, right? So it is the same. So this is b of t. Okay, so it is the same as the separating of the variables. But this is the general solution. Okay, so you should be able to derive particular solution given the IVP. Okay, so IVP will give you the particular solution. Right? So now, putting in, when t is 0, b is 2. When t equals to 0, b is equals to 2. So 2 is equals to c e to minus k 0. E to the 0 is 1. So therefore, our c is equals to 2. Therefore, your b of t is equals to 2e to the minus kt. Okay, and t is always positive lah. Alright, and remember, just now k is positive. Okay, so when we should be able to visualize this. Okay, so this is your t, that is your b of t. Okay, so when t is equal to 0 from starting of the problem, the amount of b is 2. Let's say here, the amount of t is 2 gram, and the question asks for what can you say about the amount of the substance in the future. So this is the question. You were not from the questions you were not asked to find to solve it or to find B, but of course you have to find it so that you can answer this problem. What can you say about the amount of the substance in the future? So when t goes to infinity, so what happened? Right? So it starts from when t 0, B is 2, and we can see that here the exponential function is decreasing. So we're gonna have, as t goes to infinity, your b of t is equals to 2e to the minus kt, and the amount is decreasing. Okay, so that's the first problem. I think this is a very familiar problem. I think during your high school, during your matriculation, you have go through this problem. Okay, so we look at the next problem, which is the mixture problem, and this is very popular questions at a higher level. Okay, alright. So again, you have to understand what does it say. Let's read first the problem. A 200-liter tank. You have a tank contains a 200 liter of pure water, has a brine mixture or the salt solution with concentration of 4 kilogram per liter. The concentration is 4 kilogram per liter, entering at a rate of 2 liter per minute. At the same time, the well mix contents drain out at the rate of 2 liter per minute. Okay, again, you have to find, this is the question, you have to find the amount of salt in the tank at any time t. Since the question says that you have this tank contain I don't have the picture. Where's the picture? There should be a picture here, but there's no picture. Okay, I'm going to draw the picture for you. Okay, so let's say we have this tank, 200 liter tank, okay, pure water, and we have a salt solution goes into the tank. So this is salt solution, salt concentration with, of course, water go into the tank, and after a while a well mix content, once you put the salt in here, okay, and we stir it, and the well mix content is being drained out at a certain rate. Okay, so we have concentration of 4 kilogram of salt, 4 kilogram per liter, and entering at a rate of this flow, entering at a rate of 2 liter per minute, and the well mix salt solution is being drained out at a rate of 2 liter per minute as well. And you have to solve the problem. Okay, so let's do the same as what we did previously. You name the variables. Since the problem talks about the salt solution goes into the tank and well mixed, and then we take out, we drain some of the solutions. So they are talking about the salt solution. In this case, it is garam in bahasa. That's why we're using this G of T, G for garam. Just now B is for bahan or substance. You can name it whatever that you want. So in this case, we use G, or you can use S, salt, stand for salt, is okay. Okay, and the salt solution depends on the time. When we drain in and when the rate flow in and when we drain it out. So the variable is T. So therefore we're going to name our function. You can name any function as you want. Okay. In my case, I'm going to name it as G of T. So G is the amount of salt at any time T. You have to tell me the definition so that I know what is your variable when you solve it. Okay, so you have to name your I will give points for the name of the variables so that I know, you know what is the variable and what is the function. So you have to tell me. That's why I give you marks. Then if G is the amount of salt at any time T, then dGdt is the rate of flow. Flow in minus flow out. Okay, so now when T is 0, there's only water in the tank. Okay, there's no salt. When T is 0, there is no salt in the tank. When we start the countdown, then the salt solution goes into the tank. Okay, so we have the IVP when T equals to 0, G is equals to 0. There's no salt in the tank at starting point. Okay, so I'm going to add in a page. Right. Okay, so we have the rate of change of the salt solution is given by the rate in flow. Okay, so the rate in minus the rate outflow. Okay, so this is conservation equation or momentum equation. The rate of change of anything is equals to whatever rate in minus rate out. Okay, it is a balance equation, conservation equation. Okay, so what is rate in? We have 4 kilogram here, 4 kilogram per liter. Let me use green color. 4 kilogram per liter of rate flow. And what is rate in? Rate in is 2 liter per minute. That is the rate in of water minus what is the rate out? What is the amount of salt? We have 2 liter per minute, right? 2 liter per minute. That is the rate out. And what is the amount of salt that is being drained out? Since the salt solution is being we put into the tank, right? So we're gonna call just now G of T. The salt solution is in the tank. So when G, whatever the number is, we don't know yet. Do we know? Yeah, we know. 4 kilogram per liter. Okay. We put into the salt solution. So the amount is 4 over 200. Right? Whatever the amount in the tank, before we drain it out, it is 4 kilogram per liter multiplied with 200 liter. Okay, but that is the amount of salts. But when we drain it, we don't know how much of this salt being drained out. Okay, so we're going to call it as G of T per 200, right? Because it is being diluted by the amount of salt in the tank. Okay, so G over 200 is the amount of G of T. I'm going to put it as G, is the amount of salt in the tank at any time T. You didn't drain it out yet. So when it is the salt solution is being drained out, G of T is multiplied by 2 liter per minute. That is the amount, the rate of outflow. Okay, so now we have, if you look at the units, so G is in kilogram, right? The amount of salts is in kilogram and time is in minute, right? So to make this equation correct, so whatever the unit on the left hand side here, kilogram per minute, the same with the right hand side. Okay, we'll see. So this is liter. So we have 4 multiplied by 2 is, it is 8 kilogram per minute, right? So that is correct. Minus, so 2, this is 100. So liter, this is liter as well. Liter cancel out liter. So we have G is in kilogram. So G over 100. We have this one is kilogram per minute, right? So it is correct. So now we have dg dt is equals to 8 minus G over 100. Or change it into standard form, first order. So we have dg dt plus whatever involved with the variable we put on the left hand side. Whatever doesn't involve with the variable, you let it stay on the right hand side. So G over 100 is equals to 8. Now you have first order differential equation, linear with non-homogeneous. Okay, non-homogeneous linear first order ordinary differential equation. Again, you can solve it using the separable, if you can separate it, just like we did in the first example. Or you can use, as I said, the integrating factor is the best solution because it works with all kind of equation. So I think I'm going to use that. Okay. Since we have this equation in standard form, right? Now your function is G, your variable is T. Okay, this is your variable, this is your function. Okay, so you're using the integrating factor method. So we have identify first your P of T is equals to 1 over 100. Your Q of T is equals to 8. Right? Now, integrating factor method. So we have rho of T. Remember your variable is T. So your rho is with respect to the variable that we are using. So rho of T is equals to e to the power of P of T dt, or equals to e to the power 1 over 100 dt. Okay. So we have the integrating factor is e to the power of t over 100. Okay, shortcut d dt of what is your variable G multiply with rho of t is equals to rho of t multiply with your Q of t, right? And then integrate both sides. So we are going to have d dt of G multiply with e to the t over 100 is equals to right hand side is 8 multiply with e over t over 100. Okay. And oops, sorry. And now integrate both sides. So we're going to have G E T over 100 is equals to 8 multiply with you are integrating e to the power of 1 over 100. So we're going to have multiply with 100, 1 over 100. So multiply with 100. Okay. So we have 800 e to the t over 100 plus c. And divided by e to the t over 100. So we have g of t is equals to 800 divided by e to the t over 100. So we have 800 plus c e to the power of minus t over 100. Okay, so this is the general solution. So we have our IVP when t is equals to 0, so g is equals to 0. So put into the equation, so we have c is equals to minus 800. Right now, put back into the equation. So we have g of t is equals to 800 minus 800 c e to the minus t over 100, or I can take 800 out. So we have 1 minus c e to the power of minus t over 100. Oh, sorry. C is 800. No. Okay, wait. Oh, sorry. Okay. Right. Okay, so now, so that is your g of t. So this is your solution. So let's check. It says that when we put the solution inside, the amount of t is 4 kilogram, right? So when I put the solution into the the salt into the water, the tank. So the amount of salt at any time t is g over 200, right? So let's say we have g at any time t, right? G over 200. So this one divide by 200 as well. So we have when t goes to infinity. So we have g over 200 is equals to 4. So this is 4 kilogram. Okay. So that is correct. At any at the initial time when we put the salt, the amount of salt amount of salt concentration is 4 kilogram. Okay. So this is when t goes to infinity. Alright. Next, we have this prediction population. Okay, so prediction population is very important. This one we use a Malthus equation, Thomas Malthus population equation. So we have few examples of a few models of the population, prediction population. So this is one of the easiest example, whereby it says that when the rate of change of the population is increasing. So when the population is increasing, therefore why we do the prediction? Because we need to prepare the all the for example hospitals, all the facilities for the citizen. Okay. The number of hospitals, number of schools, for example. Schools is very important when the population is booming, so we need all these facilities, hospitals, schools, what else? I don't know, maybe a number of beds, for example, at the hospital. Okay, not only the number of hospitals, but number of beds, for example. Okay, therefore prediction of population is very important. But on the other hand, when we have this COVID-19 recently, and we have a decreasing of population, because so many, the number of death is higher than number of birth. Okay, so we are using the rate of population. It's about the same as the rate inflow minus rate outflow. That is the rate of change of the population. But in this case, we're using the rate of birth minus rate of death. Okay. Therefore, during the COVID-19, the number of population is decreasing because the number of death is greater than the number of birth population. Okay. So let's say again, the problem talks about population. So we have to call your function, whatever, name your function, whatever. You can use y. You can use y of t, but to make it understand better, so we're going to call it as p of t. P represent the population. Okay. Let's say p of t is the population at any time t. So we have the birth rate and also the death rate. Okay, so the birth rate is equals to I'm going to use alpha, okay, multiply with the population, and the death rate I'm going to use beta multiply with the population. So that is the amount of the birth rate and also the death rate. Okay, so at any given time t, very small time t, so delta p, very small time t, so delta p of delta t is equals to alpha, the rate of birth rate minus the death rate. Okay, or the change of the birth rate and the death rate is alpha minus beta multiply with the population. Okay, so that is dp over delta t. Oh, sorry, very small change, so delta t over delta t. So this is equation for the rate of change of population. So let's say we can rename this the rate of change. Since there is a rate of change, you can you can have each country every year the DOSH, the Department of Statistics, will produce a report where it will state what is the birth rate of Malaysia and the death rate of Malaysia. And each country, they have their own birth rate and also death rate. Okay, so we can use that to model the number of population. So once you get the number, you will get the constant rate. So I'm going to call the constant rate as gamma. Okay, so gamma is the difference between the death rate, the birth rate, and the death rate. Okay, so a simpler model, we're going to have dp dt is equals to gamma p. Okay, very simple population, very simple model. Alright, so you can solve this using separating the variable. I'm not going to do this. Once you have ln p, so take exponential function both sides. So we're going to have p of t is equals to k e to the gamma t. Okay? Just as what we did previously. So that is number of p. For now, that is the general solutions. So to find the particular solutions, so you can put in data. Let's say this is very old data. Again, as I said, you can refer to this. I took this from the DOSH report of DOSH, Department of Statistics. So you can get this report, the current number of population, and then you can predict. For example, we have, let's say I'm going to assume T is 0 at 1980. So we have population of about 13.7 million. So 10 years later, so the number, so when t equals to 10, since t equals to 0 is 1980, so for 1990 is 10 years later. So 10 years later, the number of population is 17.76. Alright? And but when I took this data, we have up to 1995. Okay? I did these notes in 1997. Okay, so in 1995 we have about 20.69 million. But remember, our time frame is every 10 years. So I want to know what is during this time, 1997, I don't know what is the number of population in the year 2000. So we don't know the number of population. So you can use this T0, T10, and you can predict at another T20, 20 years later from 1980. Okay. So you just put into the equation, you should be able to solve it, and then P1 is when T is 0, P1 is at 1990. Okay, that's P0. So this is P0. So this is P1. So this is P2. Okay. So P2 at year 2000. So prediction for the year 2000 using Malthus equation, it is 22.9 million. I think it's about right. Okay. But maybe year 2020, 2030, if you want to predict, it will be a slight difference since we have COVID-19 recently. Alright, so determine the time of death. This is if you watch CSI, okay. So you have to determine the time of death. Alright, again we are using about the same model or the same conservation of equation. Okay, let's say we have this investigation of homicide or death case, and we are going to use this Newton's law of cooling, where it says the temperature of a body changes at a rate that varies between body temperature and ambient temperature. Okay, the rate of change of a body, temperature of the body. So we are talking about temperature here. So your function you can use as T. Okay. Oh no, I'm not using T because I'm using the ambient temperature as well. Okay. So I'm using a different variable. You can use any variable. You can use Y if you want to. So in this case, we are using delta. Delta is the temperature of the body at any time T, and big T is ambient temperature. So the rate of change of the temperature of a body is equals to the current temperature minus the difference between the current temperature minus the ambient temperature. Okay, so this is temperature of the body. Again, you have to define theta is the temperature of the body at any time T. Okay, temperature of a body at any time T. Okay, and big T is the temperature of the ambient temperature of the surrounding big T. Okay, so the rate of change delta with respect to T is theta minus T. Okay, the difference between the temperature of the body with the ambient temperature. And remember, our body temperature is always equals to the ambient temperature. So when somebody died, the temperature of the body is it is cold, right? So it means that the temperature is reduced. Okay, therefore, when we say that the delta, the rate of change of the temperature of the body is proportional to theta, the difference between the temperature of the body and ambient temperature. So to make it equation, so we have to write it using equal sign, K of theta minus T. But since the body temperature is reduced, so we add the minus sign. Okay. Okay. Oops. Minus K. Okay. So that is our model. Okay, now the problem is, let's say at time t is 0, when we find the corpse, when t is 0, the temperature is at a certain number. Usually when you watch the CSI, okay, they will come and they will measure the temperature of the corpse at that time, and they will record that time. So that time we're going to consider it as T0. Okay, so when we want to know what is the time of death, okay, and we can calculate it, right? So here it involve theta, and here we have theta, and big T is constant, so we can separate this. D theta over theta minus T is equals to minus K dt, and you can differentiate this. Okay, so you should be able to solve this. And using the known variables, suppose the time of death is Tm, you don't know that, and temperature of the body, you know that delta M, okay, you know temperature of the body when you found the body, and you also know the body temperature, the normal temperature, the ambient temperature. So we should be able to solve this. Okay, so I'm not going to show this. So once you find the K, put the K in, so you should be able to estimate the Tm. Okay. Alright, so another example is a mechanics example where we have this an object. Either object is, when you throw an object, it will go downwards. Okay, either you throw it, let's say I have a stone here, so if I throw it that way, so it falls using the projectile motion, or if I throw a stone going upwards, and it will go downwards as well. Okay, so whatever the case is, the object is always falling downwards. Okay, let's say we have an object with mass m. So this stone with mass m move with the effect of a force, because you throw it. Okay, so we have a stone being thrown upwards, and then it goes downward. Okay, and you have a friction force, the wind, for example, that is the friction force, and this friction is always move opposite of the direction of an object. Okay, and it says that the friction force is proportional to the speed of the moving object. Alright, so let's say we have you're going to use this Newton's equation, summation of F is equals to MA, because an object is moving, so summation of F is equals to MA. Whatever F is, F can be, let's say, the weight of the stone, W equals to mg, so this is kind of force. So what are the forces that you have when you throw the object, when you throw the stone? So we have friction force, and it always move opposite of the movement. So when the object move upward, the friction move downwards, Fg. Okay, so we have, let's say you have to have a reference frame, okay, just to make sure that your direction of all the forces is the same. That's why you have to have this reference frame. Okay. Oh, sorry, in the example, a stone is dropped from rest. So the movement, I'm going to, yeah, okay. So the movement is going downwards. So the stone is dropped downwards. Okay. So the movement is going down. And since the movement is going down, I'm going to use my positive, my reference frame is going downwards. Positive is downwards. Alright, and just now friction must be opposite of the movement. So friction is going upward and weight is going downward as well. Okay, so we have summation of, I'm going to add a page. Right, so we have summation of F is equals to MA. What F do we have? Going downward is positive. W is positive, going downwards. And what else? Friction, going upwards, so it is negative minus Fg. Actually, this is all F1 plus F2 plus F3 plus dot dot dot. All the forces, Fn is equals to Ma. Okay, so in this case, F1 is equals to W, F2 is equals to Fg. So W is positive, Fg is negative. So that's why we have W minus Fg is equals to Ma. Okay, Ma. What is the direction of motion? Going downward. So A is positive. Let's say my direction of motion, my direction of motion is the same, but my reference frame is positive outwards. I'm going to use the convention one. To the right positive, going outward positive, but the movement is negative, so W is negative, Fg going outward positive. What else? The movement is A going downward. So I'm going to have summation of F equals to Ma. So what do we have? W. So since our direction is positive, so W is negative, Fg is positive. So I'm going to write positive first, minus W is equals to M. A going downwards, our reference frame is going outwards, so minus Ma. Okay, so you're going to have the same results even though the direction is different, but this one is important. This one determine your direction of motion. Therefore, in either method, you will get the same solution. Okay, as long as you know what is direction, your reference frame. So you have to tell me your reference frame so that I know. Okay, it's easy for me to figure out from the equation. If you don't, that's why I give marks on the reference frame. Okay, okay, so you can solve this. Put in all the values, you can solve. Right, so what is A? So A is dv dt, right? Again, we have a displacement x. Okay, and we derive x. We have v, so this is velocity. You derive x again, squared. Dt squared. Or derive v, you'll get acceleration, right? Or this is equals to A. Okay, so A is dv dt. So I'm going to replace back W equals to mg minus f of g. Oh, okay. It says that the friction force is proportional to the speed. Friction force is proportional to the speed of the object. Okay. F is equals to v. So what is v again? So v is the velocity just now, right? V is the velocity. So v. So change it into mathematical form. We have kv. Fg equals to kv. Okay. Right, and I'm going to write this kv as like that. Okay, but it's okay, it doesn't matter. All right, so Fg is kv. Fg is kv is equals to m. What is A? dv dt. So now we have the equation in terms of v. So rearrange that so that you have in a standard form. So you have m dv dt plus kv is equals to mg. Make it a standard form divided by m. So we have dv dt is equals to plus k over m, constants v is equals to g. So this is first order linear differential equation. You should be able to solve this. Okay. Again, you have the given if the problem state that when a stone is dropped from rest. Okay, that's your IVP. A stone is dropped from rest. So when t equals to 0, v is 0. There's no velocity. Okay, because it doesn't move yet. So when t is 0, v is 0. So put your IVP here. When t is equals to 0, v equals to 0. Okay, so you should be able to solve this. Alright, I think, yeah, that's it. Alright. So, thank you.